So I'm going to hand this over now to Dr. Wang. If you have any issues hearing, please let me know in the chat box.
Thank you, Maria. I'd like to share my screen. Give me 1 minute. Well, I hope you can see my screen now. Looks fine. Okay.
Yes, it looks, if you're on the same page, the About EIT page, then yes, we're seeing your screen.
Yeah, exactly. Okay. Hello, everyone. Thank you for joining with me for this technical webinar by Engineering Institute of Technology, EIT. I'm Dr. Xiaxia Wang, a civil engineering lecturer here at EIT based in our Melbourne campus. Over the years, I have been working on cement-based materials, behavior of high-performance high-performance concrete against severe loading conditions. And I'm also very interested in green concrete and low carbon concrete structures. Today, I'm here to share with you some information about sustainable materials and the practices in civil engineering and particularly in construction sector. This is the agenda items for today. Firstly, we'll discuss why there is a need for sustainable materials and the practices in construction sector by looking into the impact of construction activities on climate changes. And next, I will share with you some strategies to decarbonize construction materials and the relevant activities following the 3 principles of avoiding, shifting, and improving. And finally, we will look into relevant policies and other measurements towards decarbonization of the construction sector. Now, let me start with addressing why do we need sustainable materials and practices? Well, to answer this question, I need to start with global warming and the greenhouse gases emissions. Global warming is the unusually rapid increase in Earth's average surface temperature over the past century, primarily due to the greenhouse gases released. Studies show that 2,590 gigatons of carbon dioxide have been emitted since 1850. The remaining carbon budget to limit global warming to 1.5, 1.7, and 2 degrees Celsius is 275, 625, and 1,150 gigatons of carbon dioxide, respectively, which are equivalent to 7 years, 15 years, and 28 years from today, 2024. There is an urgency for us to reduce the carbon dioxide emissions to meet the goal of the Paris Agreement. This chart shows the breakdown of total greenhouse gases, which is the sum of all greenhouse gases measured in terms of carbon dioxide equivalent by sector. So as we can see, electricity and the heat production are the largest contributors to global emissions. This is followed by transportation, manufacturing, construction, and agriculture. The building and the construction sector is one of the largest contributors to climate change, responsible for more than 1/3 of global energy-related carbon emissions. In the absence of urgent action, the carbon emissions of common construction materials such as concrete, steel, and aluminium are projected to grow to increasingly dangerous levels. Even with the implementation of widely accepted interventions, emissions from the construction and the building sector are projected to go far beyond what is allowable to keep global temperature rise within 1.5 degrees Celsius, which is the target set under the 2015 Paris Agreement on climate change. Well, to reduce the carbon footprint from building and construction, it is important to understand how and where most of the greenhouse gases emissions are generated. These emissions are broadly split into 2 categories, embodied emissions and operational emissions. The embodied emissions are all the emissions associated with the construction and deconstruction of a building, transport and on-site construction of building materials, and at end-of-life demolition or reuse for new buildings, in which the production of building materials makes up the largest share of the embodied carbon. Then operational emission. Operational emissions are the emissions generated through their function, for example, heating, cooling, and lighting, and as well as their maintenance of the building. The initial design choices for buildings, such as the building materials used, as well as the upgrading materials during the renovation, have significant impact on the amount of operational carbon and on the opportunities for recycling. In recent years, considerable attention has been focused on how to reduce the operational carbon in the built environment, and the share of the operational carbon will shrink as electricity grids increasingly transition to renewable energy, and as building operation can become more efficient. Until now, most of the progress in the sector has been made on reducing the operational carbon of a building, which are projected to decrease from 75% to 50% of the sector in the next few decades. However, solutions for reducing the embodied carbon emissions from the design, production, and the deployment of the building material have still lagged far behind. Now, you may ask, what materials do we use? This picture shows the global material consumption in 2017 and the outlook consumption to 2060. As we can see from the figure, in the coming decades, growing population will drive a strong increase in global demand for materials. Global materials use is projected to more than double from 79 gigaton in 2011 to 160 gigaton in 2060, in which the non-metallic materials such as sand, gravel, and the limestone represent almost half of the total materials used. Materials used in construction is a very large part of non-metallic materials used, or in other words, we would say construction materials dominate total materials used. Well, of course, the construction sector also uses other materials such as metal, aluminum, and so on. Now let's have a closer look into the non-metallic materials. Another study also shows that the construction materials use is projected to almost double between 2017 and 2060, with the largest growth in sand, gravel, and crushed rock. Their use will grow especially rapidly in the short run, given their strong links to investment and the construction needs and the lack of high-value recycling. This significant increase follows directly from the close link between economic development, investment, infrastructure, and the construction. The growth in materials use, coupled with the environmental consequences of material extraction, processing, and waste, it is likely to increase the pressure on the resource basis of our economies and also jeopardize future gains in well-being. So therefore, recycling is projected to become more competitive compared to the extraction of primary materials. Now let's have a look at the carbon footprint from different construction materials. The production of building materials and the construction activities cause roughly 10% of global energy-related greenhouse gas emissions, and the manufacturing of cement, steel makes up almost 3/5 of these emissions. Globally, cement and steel are the two of the most important sources of material-related emissions in construction. Other conventional materials like aluminum and glass and some other insulation materials also cause high emissions. Well, data also shows that the construction sector, okay, is by far the largest emitter of greenhouse gases, responsible for 38% of the world's global carbon dioxide emissions, of which 30% are linked to building materials. The emissions associated with materials and the construction processes needs to be tackled to avoid undermining energy saving measures. And well, as we may know, global cement consumption is projected to increase by maybe 20%, okay, by 2050, and while the global steel production is forecasted to grow by almost 30% over the same period. So it is important to recognize the crucial role that these materials have played and will continue to play in human society, even as we will point to the need for radical decarbonization. Well, so far we have discussed the urgency for decarbonization of the building and the construction sector. Next, let's move on to the possible strategies or principles for the decarbonization. But before I start, can I please ask you to provide me with some ideas? What are the sustainable materials or practices that you are using or plan to use, or that you think it may work? Okay, you may want to type that in the chat box. So if you have any idea, how do we, what kind of sustainable materials do we, yeah, reducing use ready to use, yeah, solar energy. Thank you, Richard Fate. Yes, use of GGBS in concrete mix. So GGBS is a kind of supplementary cementitious materials, right? Yeah. About plastic, very good. Okay, supplementary materials, again, timber. Yeah, timber is more environmental friendly than many other construction materials. Rice husk is also a supplementary cementitious materials. Reuse of steel, timber, recycled materials. Yes, very, very good. Wind energy, yeah, definitely. Masonry, yeah, very good, very good. Thank you, thank you, thank you, thank you, thank you very much. Yeah, recycled aggregate, good, good point. Thank you, thank you, thank you, thank you so much. Yeah, thank you. A lot of ideas. Okay. Sorry. Thank you to all of you. There are actually apparently a lot that we can do to decarbonize buildings and the constructions. Generally speaking, most of the approaches, including what you told me in the chat box, okay, can be actually categorized into this avoid, shift, and improve framework. Avoid means avoid is actually to avoid emissions through circularity, and the shift means that we're going to shift to sustainable materials or practices, and the improve is to improve the conventional construction materials and the practices. And we are going to discuss each of these three approaches in more details next. So now let's start with strategies to avoid embodied carbon from design to end of life and beyond. Avoid essentially means build less, design less. Basically, we need to rethink how we design, construct, and reuse our buildings in order to avoid, that is a keyword of circularity. Well, in fact, policies relevant to circular economy has been adapted by a number of countries or regions to enhance resource efficiency and to preserve the environment. The concept of circularity, as indicated in this figure by United Nations Environmental Programme, encapsulates the principles such as reuse, okay, recycling, and remanufacturing, with the approaches that can enable the closing, expanding, and the narrowing of material loop. So this actually involves reducing the environmental impacts associated with whole life cycle of resources from their extraction to their disposal. Well, as illustrated in this picture, circularity builds upon value returning loops, and the circular process can be grouped into 4 categories from the most impactful to the least. The first one is actually the reduce by design. Okay, so this is about recycling the amount of materials used, particularly raw materials. This should be applied actually as an overall guiding principles from the earliest stages of the design of the products and the services. And then from a user to user perspective, we have a reuse, okay, reduce, okay, and reuse. Then if we look from a user to business, okay, perspective, we have repair, okay, reduce. We have repair, okay, refurbish, and remanufacturing. And then finally, if we look at from a business to business point of view, what do we have? We have repurpose and the recycling. Okay. So there are actually a lot of opportunities for circular design, recycling, and the reuse at each phase in the building life cycle. So the reuse and the recovery of materials is essentially towards achieving circular production and the use of building materials. The most carbon savings at a building's end of life comes from reuse, actually. The reuse of building, okay, and then reusing the component, and then reuse materials. Okay. In the circular economy, buildings will become material banks for future construction. And after the end of life of building materials, building materials should go separated and reused. Buildings should be planned to be recycled from the outset. The whole building component might be reused, but mostly individual materials are recycled. Recycling actually can reduce the overall carbon footprint of building materials. Now, looking at the building process from a whole life cycle point of view means we have to consider all the carbon cost of material choices, from the impact of material extraction, okay, on ecosystems, to the environmental effects of production, construction, maintenance, and demolition. Okay, you can see that whole life cycle emissions are a combined measure of the embodied emissions, okay, in the building materials, and the operational emissions from the building's energy use and the energy source emissions. By making assessment and the decision about carbon impact over the courses of the entire building life cycle, we can actually allow for choices that optimize for carbon efficiency between both embodied carbon and the operational carbon. Well, the best way to reduce the embodied carbon is actually through prevention. Okay, as this figure shows, with this y-axis being their carbon reduction potential. By building nothing, okay, we can see that by building nothing, we altogether actually eliminate the potential for embodied carbon emissions. Okay, and we can see that as the project progresses, it becomes more challenging and more costly to make design changes in order to reduce embodied carbon. This page summarizes some of the avoid strategies at different stages, okay, in the building and the infrastructure life cycle. The planning stage is the key to reducing embodied carbon, as we discussed just now. This ranges from like questioning the necessity of building something new and renovate existing assets rather than constructing new ones, and mixing and optimizing uses rather than planning for single use. And we should also promote compact urban spaces rather than low density sprawl. Also, we should actually choose project size where less materials, foundation work, and the transport are needed. Okay, and when it comes to the design stage, the strategies are about materials, quantities, durability, and the recycling, including reduction of materials needed through building topology, geometry, volume, and the material saving constructions. And we should also use low carbon building materials, including recycled materials. And we should use a high durability of components and the design to reduce the need for maintenance and the renovation, and to prolong the lifetime of the building. In addition, our building should also have the adaptability to successive uses to ensure a long lifetime and reduce the refurbishment. And finally, we can look at you can see that there should be there should be less appliance, following the concepts of sufficiency, and opt for appliance with a low carbon footprint and high production efficiency. So overall, at the design stage, life cycle assessment should be used to guide design choices by evaluating and visualizing the impact of different options. And finally, let's consider the stage of construction, refurbishment, and end of use. Well, construction works as well as refurbishment and even deconstruction are actually energy intensive. So improved technologies and the smart management method can reduce the energy wastage and lower the carbon footprint. Generally speaking, optimized construction work, they can save time, energy, and money, relying on their, for example, improved construction logistics through digital management tools. And we can use modular prefabrication to save time and energy on site. Well, we should also actually use trained and well-equipped construction workers. So next, a clever refurbishment, it can actually bring efficiency gains on resources such as water, energy, and materials. And well, circular economy, this circular economy approaches and the reusing, recovering, and recycling materials can dramatically reduce the embodied carbons of a building. And investing in material recycling chains instead of disposal can optimize material use and the low transport and manufacturing costs over time. So far we have talked about the strategy to avoid. Now, next, let's look into shifting. Okay, so well, this is actually talking about use alternative building materials or shift to regenerative materials practices by using low carbon, earth-based or bio-based building materials whenever possible. Firstly, let's have a look at the timeline in material development, and we will be focusing on construction materials in civil engineering. Well, we can see that since the prehistory, people have started to use materials such as wood, stone, and natural fibers. The development of materials have been driven by industrial revolutions. For example, the first industrial revolution enabled cast iron, and Portland cement, which is the main ingredient for concrete, was invented in 1824, actually. In the second industrial revolution, materials including steel, copper, rubber, and glass replaced the older materials of construction. The third industrial revolution stimulated productivity by the wide availability of plastics and composite materials. Now we are actually immersed in the fourth industrial revolution, which is an age of functional material. Okay, as we can see, the biomaterials, including wood, timber, they actually dominated the global construction alongside with some earth-based materials until the late half of the 20th century. Okay, it has only been in the last several decades that the majority of the building materials come from extractive, toxic, or non-renewable processes. Okay, by the late 20th century, metals and mineral-based materials become the most used building materials for the first time in human history. Then this figure shows the embodied carbon dioxide and the embodied energy per kg of many different construction materials. The embodied carbon dioxide is the total amount of carbon dioxide produced in the extraction and the transportation of raw materials and their manufacturing into the final products. The embodied energy is the sum of all energy consumption, which includes the energy used for material vegetation and production, construction, installation, maintenance, and demolition. Okay, then you can see that in comparison to metals, okay, concrete, sand, and gravel actually have a much smaller impact per kg per kilo. Okay, but the volume of their use is really huge. Okay, these materials are especially associated with climate change impacts. Okay, we can see that just the three materials, concrete, okay, steel, and aluminium, are actually responsible for 23% of overall global emissions today. Okay, of course, other materials, we do have other commonly used carbon-intensive materials in construction, including, for example, bricks, okay, and the glass. Now, when we are actually selecting sustainable construction materials, life cycle analysis based on local data is very important to guide the design decisions. Okay, local cycle assessment refers to systematic analysis and evaluation of the potential environmental impacts on material production or services during their entire life cycle, from the production to the distribution, operation, and end of life phases. So the life cycle analysis of building design option is okay, I'd say is a game changer, okay, to address embodied carbon. Quantifying and comparing embodied emissions allows us to compare options for design and for materials. It is also the basis for many national and local policies and investment decisions. Okay, here now we have a keyword of local. Okay, building materials with optimal properties, okay, for local climate, okay, should be selected. Okay, for example, in a hot arid climate, okay, building materials with a high thermal mass are needed, such as clay, okay, a natural stone, or bricks. Okay, and then in other words, okay, on the other hand, in humid subtropical climate, okay, materials should allow for low thermal inertia and natural ventilation, such as timber, okay, bamboo, and some, for example, lightweight facades, and so on. Okay. And in addition to this, okay, we should also try to develop local value chain to lower their transportation emissions and strengthen the local economy. Okay. When selecting construction materials, try to use low carbon materials and avoid carbon dioxide intensive materials like aluminium or steel. And we should also use low processed materials. They are actually preferred than consuming because they actually consume less resources for production and are easier to recover and recycle. Okay, we should also try to use resistance materials with a longer lifespan, and so therefore less replacement or maintenance is needed. Okay. Also, apparently, we should reuse of materials instead of manufacturing new products. Now, you may ask me a question. Okay, what construction materials, okay, would pass this checklist, and what materials are the sustainable materials we can use in construction instead of many conventional construction materials? Okay, well, alternative sustainable construction materials range from bio-based to recycled materials. Okay, bio-based materials have been used for a very, very long time all across the globe, and they may actually represent our best hope for a radical decarbonization through the responsible management of carbon cycle. Okay. The shift towards properly managed bio-based materials could lead to emissions savings in the sector of up to 40% by 2060 in many regions, even when compared to savings from low carbon concrete and steel. Well, we can first look at wood or timber. Okay. Timber has excellent thermal as well as the static properties, and can replace steel and reinforced concrete. The source of timber is apparently trees. Trees actually can act as carbon sink, and the use of wood can considerably bring down emissions. Okay. Of course, in order to lower relevant transport emissions, okay, the use of native wood species should be preferred. Okay. And the next, bamboo. Okay. Bamboo is a fast-growing renewable resource that has witnessed significant advances as building materials in the past 2 decades. Progress in engineered bamboo have demonstrated structural performance similar to that of cross-laminated timber and steel. However, the variability in species across regions or countries requires investments in further development of low-cost and low carbon construction methods, and including standards and certifications to gain the confidence of industry for large scale application of bamboo. Okay. And then a clay. Okay. Locally sourced and unprocessed earth can actually replace concrete, and is increasingly being used as modern building materials. Clay can be processed and transformed into clay bricks or boards. Okay, because of an almost infinite capacity to be recycled or upcycled, earth building materials have a low energy balance, okay, in the entire lifetime. Okay, and well, lastly, we can look at stone. Stone is also used in construction as, for example, masonry units, or as aggregates to make concrete, etc. Well, next, I want to briefly talk about mycelium. Okay. Mycelium, okay, is actually the root system of fungus, okay, as shown here. Okay, the mycelium can be actually used as a building materials with both structural and thermal properties. Okay, it can be cultured on low-grade agricultural waste. They are actually characterized by their good durability, strength, no thermal conductivity, and high specific heat capacity, and they have good fire resistance and good acoustic absorption. Okay, so because of this convenient material properties, low cost, a simple manufacturing process, and the most importantly, environmental sustainability. Okay, the mycelium, okay, potentially will become significant in future green construction. Okay. One good example that utilize mycelium components is this hi-fi mushroom bricks tower located in New York, as shown here. In this tower, the bricks are made from microscopic fibrous fungus bounded to agricultural waste. So, okay, we would actually consider it is actually a tower or made almost entirely out of mushrooms. Okay. Myceliums can also be merged with many materials to form composites with improved mechanical and thermal properties. Okay? For example, high-performance natural insulators such as straw, okay, and hemp fibers could be added to myceliums and its composites to make a practical, low-cost, and environmentally sustainable substitute for conventional insulation materials. Okay. Straw and other plant-based products provide excellent insulating properties and are apparently less polluting than conventional insulations, and often, most of the time, they are actually 100% compostable. Okay. Other plant-based materials, including, for example, hemp, wood, wool, or flax, okay, innovative types of concrete mixing organic materials such as hemp or recycled fibers reduce the need for reinforcement. Okay. Reinforcing elements made of natural materials, okay, for example, this, okay, can actually replace energy-intensive steels to reduce the overall carbon footprint of reinforced concrete. Then I would also like to talk about recycled material. Okay, recycled material also have good potential in construction. Okay, for example, okay, concrete. Okay, concrete building components can be crushed and reused as an ingredient for concrete, and can substitute up to 45% of the gravel in concrete. However, the return rates of secondary raw materials for concrete production are still below 60%, and the application field is so far limited to low-grade concrete, in particular because of the relatively low quality of the available secondary aggregates. Their exchange rate for primary material is limited to about 30% nowadays. Overall, the state-of-the-art recycling has so far been rather downcycling, okay, for recycled aggregate, and the concrete produced of the obtained secondary material even sometimes may compromise it slightly, increase the global warming potentials. So there are a lot of studies going on nowadays trying to overcome these obstacles. Okay. Then we can also recycle steel or metal. Okay, while steel can be made by recycling of metal scraps, the application is still limited by the availability of metal scraps. Then plastic. Okay, every year the world actually produces around 400 million tons of plastics, of which only roughly 9% get recycled. Okay. Converting this plastic waste into building materials offers a huge potential to increase the lifespan of previously unrecycled plastics. Okay. For example, we may see that nowadays plastic waste have been used into, for example, waterproof bricks in some places. Okay. And finally, glass. Many applications have arisen to integrate this recycled glass actually. For example, glass powder, okay, is used to integrate into concrete. Glass is also used in concrete as aggregate or glass fiber reinforcement. Okay, so there are actually, of course, a lot of other possibilities to use alternative sustainable materials in construction for those who want to explore even further. Okay, but now we need to move on to the third strategy by improving conventional building materials and the processes. Okay, so in this section, we will focus on how to decarbonize concrete, okay, which is the most used construction material in the world. Well, studies have revealed that we can actually reduce emissions from concrete by about 80%, okay, with known technologies if we make the most of these approaches. Okay, firstly, we can look at reducing carbon dioxide from clinker production. So there has been a tremendous achievement in the efficiency of cement plants, okay, over recent years, and the production process is highly optimized up to around 80% of the thermodynamic limit. Of course, there are still possibly some room to improve, but not very much and very difficult. Okay, we can of course also replace fossil fuels with biomass and other waste fuels to operate our cement kilns, or shift to electrical kilns powered by decarbonized electrical grids supplied with, for example, renewable energy. Okay, generally speaking, this has actually been largely done because our cement kilns nowadays are very efficient, and this is relatively easy to implement. Okay, we also briefly talk about innovative no emissions raw materials, including calcite claim in this webinar soon. Okay, then we can think about reducing the clinker content in cement, which can be done by introducing mineral admixtures, including supplementary cementitious materials. Okay, like many of you actually pointed this out just now in the chat box, but it doesn't actually stop there, because we should also think about reducing, okay, the amount of cement, okay, in concrete, and this can be as simple as optimization of concrete mixture design by using good aggregate sizes and good grading, and we can use appropriate mixtures, okay, and fillers, and select a good choice of water to cementitious ratio. But it is very difficult to inform so many millions of concrete producers about these ways to save cement in concrete. Then, of course, we can reduce the concrete in building, but this is also quite difficult to implement because this complex the chain of decision makers. So as much as 25% of emissions from cement and concrete can be readily saved by adapting building codes and by educating our architects, engineers, and builders to use the best available technology. And then, of course, we should actually reduce buildings or increasing or mandating fabrication of circular units, okay, that can be disassembled and can be reused for future building. Okay, however, till today, the biggest opportunity to really achieve emissions reduction fast is to reducing the clinker, okay, in cement, because Portland-based cement will continue to dominate, and using supplementary cementitious materials, okay, is one of the most realistic options to reduce carbon dioxide at least for the near future. Okay. So this picture actually shows some commonly used supplementary cementitious materials from left to right. They are Class C fly ash, metakaolin, or in other name, calcite clay. And we also have silica film, Class F fly ash, okay, GGBS, ground granulated blast furnace slag, GGBS, or slag cement. In some countries, we call it slag cement. And lastly, calcite shell. Of course, there are many other supplementary cementitious materials. For example, rice husk ash. Okay, sometimes we may even use bleached glass. And in addition, for example, we have many other natural pozzolans and limestones and so on. Okay, so the practice of using supplementary cementitious materials in concrete admixtures has been growing since 1970s. Okay. Generally speaking, supplementary cementitious materials are added to concrete as part of the total cementitious system. Okay. Typical practice uses supplementary cementitious materials as an addition to or as a partial replacement for the hydraulic cement in concrete. Traditionally, okay, supplementary cementitious materials were used in concrete individually with Portland cement. Okay. However, there are benefits in using more than one supplementary cementitious materials in combination with Portland cement to produce concrete mixtures. Okay. For example, we have tertiary blends. Okay. Tertiary blends actually contains Portland cement plus 2 supplementary cementitious materials. Okay, they are often used when where special properties are required, and also we even have quaternary blends, which consist of Portland cement plus 3 types of supplementary cementitious materials. So these are already being used, okay, in practice. Next, I want to briefly talk about Portland limestone cement, or PLC. PLC is actually not something new. Okay, it was first developed in Europe in 1960s, and the first PLC application for paving took place in US in 2007 or 2008, 2007 perhaps, and it is now used in many countries as the preferred cement products due to the fact that it actually reduces the carbon footprint of a concrete mix significantly. Okay. PLC looks very similar with Portland cement. The difference between these two is that, okay, in addition to clinker, okay, and gypsum, okay, used for Portland cement, okay, we also add limestone. Okay, when we grind those clinker and gypsum to make this PLC. PLC is essentially a type of blended cement. Okay, standards in different countries specifies different percentage of limestones that can be added into the PLC. Some of them are actually listed here. Okay, typically it is between 5 and 15% of limestone. The product itself performs the same, okay, as the standard concrete, but it comes with great benefits. Okay, this PLC are actually in commonly used around the world nowadays, and it is actually a proven solution for reducing carbon dioxide of cement without sacrificing the performance. Nowadays, there are still some barriers preventing more widely used application of this PLC, such as the lack of education and training, and for example, supply chain restraints and so on. In addition, I would like to briefly talk about another emerging trend, which is limestone calcined clay cement, okay, or LC3. Okay. LC3 is a new type of cement made using, we can see limestone, okay, and the low-graded clays, which are available in abundant quantities, okay, and it is actually cost-effective and does not require capital-intensive modification to existing cement plants. So this is actually a typical composition of LC3. We can see that when this limestone when the limestone is added into this cement and this calcined clay blends, there will be actually the synergic effect. Okay, the synergic between these two supplementary cementitious materials, they are actually limestones and calcined clays. Okay, would actually enable higher clinker substitution. Okay, with an improved performance both in terms of their mechanical properties and the durability. Okay, low energy is consumed in this calcination, okay, at low temperature of the clay, so which is actually at the temperature roughly about 750 to 850 degrees Celsius. Okay, so it's apparently much lower than that for clinker. Okay, for clinker we should actually reach a temperature of 1450. Okay, so as a result, okay, this LC3, okay, can reduce carbon dioxide emission by up to 40%. Okay, most importantly, performance of this LC3 is equivalent and many times, okay, even better than that of ordinary Portland cement, OPC. Okay, some research have indicated that, okay, LC3 production cost is up to 25 to 30% lower compared to ordinary Portland cement production. Okay, so therefore LC3 could be one of the best solutions to our goals for sustainable concrete. Well, the production of cement results in process emission, okay, of carbon dioxide from the chemical decomposition of carbonates. Okay. However, during its lifetime, okay, cement would reabsorb, okay, some carbon dioxide from the atmosphere, okay, capturing Carbon okay, in concrete production is an active area of research around the world. Okay. However, the exact amounts of carbon dioxide that can be absorbed by concrete are still uncertain. Okay. Estimations vary, but it appears that about 10 to 20% of original embodied carbon can be reabsorbed during the service life of the concrete. Okay. Research is also going on into how to actually make concrete more sustainable on carbon absorption concrete using magnesium sulfate, okay, for example. Okay, and a lot of innovations are still in the trial stage, I would say, okay, and it needs to be improved. Okay, there are also some technologies for carbon dioxide injection and curing, okay, but also still at an early industrial scale. Okay, it is likely best for blocks, okay, and precast plants, and it could actually produce carbon negative concrete by completely offsetting the embodied carbon in the concrete. Okay, so this is a possible trend. Okay. Now, we can also, of course, use some waste materials in concrete to make it even more green or even more sustainable or greener. Okay, for example, the consumption of facial masks has significantly increased worldwide since the pandemic. Okay, so there have been studies using the wasted mask in fibrous or crushed form to produce environmentally friendly and affordable green concrete. Studies show that, okay, the addition of this waste mask would improve their compressive and tensile strength. It would reduce the chloride permeability and increase the free and zone resistance of concrete. Okay, by utilizing waste masks to produce this improved concrete with better strength and higher durability, we can actually achieve circular economy, right? Circular economy and the sustainability are achieved, okay, along with the efficient waste management. Okay, and concrete industry also has the potential to contribute significantly to increasing the recycling of some organic waste, such as used coffee. Okay, globally, okay, people drink over 2 billion cups of coffee each day, and we'll end up with roughly 60 million tons of coffee grounds every year. Only a very small portion of this is reused, okay, mostly as soil fertilizer, okay, with the vast majority ending up in landfill. Okay, so in a recent study, researchers roasted the spent ground coffee in the absence of oxygen, and they obtained something called biochar. They added this biochar to concrete as a replacement of sand, and it provided, okay, about 30% increase in the strength of the concrete. Okay, so this is another example of using waste in concrete. Okay, there are so apparently there are a lot of other opportunities. Okay, next I want to briefly talk about decarbonizing some other conventional construction materials. Okay, let's start from steel. Okay, improve the quality and the collection methods of scrap steel is very crucial. Okay, and also shifting from a blast furnace to direct reduce the iron technology could reduce the carbon dioxide emissions from primary steel production, particularly if coupled with a shift to renewable electricity sources. Okay, and next, aluminium. Okay, aluminium. Okay, roughly around 30, okay, around 30% of all aluminium produced is used in buildings and construction. Aluminium production is highly energy intensive, okay, when produced from ores. Okay, whereas producing aluminium from scrap can reduce the energy demand by 70 to 90%. Okay, by the year of 2060, aluminium production could be mostly based on scrap, and the production could be electrified using renewable energy sources. Okay, so next is plastic or polymer. Plastics are materials with high growth rate and low recycling. Okay, use bio-based and biodegradable plastics produced using with renewable energy would greatly actually reduce the emissions from plastics. Okay. Glass. Okay, next, not glass. Options for decarbonizing glass productions include switching the energy sources. Okay, electrification of all processes. Okay, and the processes intensification and waste heat recovery. Okay, in the renovation and deconstruction, okay, we can actually try to use off-site window disassembly. Okay, this would actually help us avoid contaminate and allow for glass recycling. And lastly, earth-based masonry. Well, high quality earth-based masonry has potential to replace concrete in many low-rise build applications, but needs development and regulation. We can actually replace high carbon cement binders, okay, with low carbon alternative binders. Okay, if locally made with low carbon binders, additives, and processing method, the earth masonry, okay, can regain its role as a viable building materials for many regions and applications. Now, so far, okay, we have talked about the reason why we need sustainable materials and the practices, and the different strategies to decarbonize through the whole life cycle of buildings and the construction sector. Finally, I would like to briefly discuss the roles of policy, okay, and some other measurements for decarbonization. Well, key stakeholders, okay, whose participation is critical to the decarbonization of the buildings at different life phases, they include scientists, okay, architecture and engineering and the construction companies or firms, okay, building occupants and the waste management and the recovery professionals. Okay. Active participation across these different stakeholders is essential. Okay. Access to correct information is also key for data-driven policies. Okay. Financial instruments and the research incentives to support each phase of this building and material life cycle and for each stakeholder groups. Without dedicated policies or dedicated support, sustainable building materials will not get into the mainstream. Okay. Embodied carbon targeting policies are necessary for business environment that tackles embodied carbon. In the absence of an effective price on carbon, a couple of measures are needed to incentivize and accelerate the shift. Okay, the first one is policy. Okay, for example, there are different types of policies. For example, in terms of regulation, national policies are needed for addressing embodied carbon by imposing life cycle emission reporting requirements, okay, setting, for example, setting limits to the embodied carbon contents of building parts and the building components, or specific strategies and policies addressing the highest emitting materials such as cement and steel. Okay. The flowchart on the right-hand side summarizes what policymakers can do to decarbonize construction sector throughout the building life cycle. The second measurement is finance. Okay. Financial decisions are fundamentally influenced by policy. Possible financial incentives may include, for example, green building program that provides financial incentives to buildings that meet embodied carbon criteria, as well as incentives such as tax rebates to manufacturers for low carbon building components or products. Okay. Of course, there are a lot more. Other measurements including knowledge and capacity. Knowledge about how to construct with or certify and sell low carbon materials is needed to transform this market. Okay, for example, okay, design and deconstruction professionals need to build up expertise about life cycle analysis, okay, low emissions material and the material saving techniques, okay, and for example, national testing laboratory and the facilities needs to gain experience with low carbon materials and the innovations, okay. In addition, okay, data with country-specific information on the properties of building materials are needed to calculate emissions as the basis for the regulation and the financing. Okay, such databases are not available in most developing countries nowadays. World Green Building Council set out actually very ambitious high-level pathways for business, government, and the civil society to follow, okay, in order to reduce embodied emissions across associated with our sector. Okay. A summary of the goals and the target dates for key actors, okay, in the value chain is given in this picture. Okay, hopefully this will help transform our sector from a major cause into a major solution, okay, to the climate emergencies, okay, securing a safe future, okay, for this generation and for generations to come. Well, progress on buildings and construction policies remains relatively slow, okay, in the factor, because of, for example, in the factor of pandemic, okay, and the lack of actions, and the emissions are not, okay, as a result, emissions are not really being reduced, okay. To date, okay, 158 out of 196 countries, okay, which is roughly 80%, okay, reference buildings as the part of their nationally determined contribution action plan, and only 40%, okay, have building energy codes, okay, though only about 26% of countries have mandatory codes for all buildings, okay. Decarbonization the global building stock is a very key step, okay, towards fulfilling the commitments of the Paris Agreement. Okay, building energy codes have a central role to play in improving buildings' energy efficiency and reducing carbon emissions. They also allow governments to mandate standards for the construction and the maintenance of the building. Okay, there is an continued recognition of green building certification system across the world. Building energy and the sustainability rating systems are continuously evolving to address the net zero emissions and have established the criteria for the assessment of sustainable actions. Okay, these certifications provide growing evidence of the progress being made by the buildings and construction sectors towards sustainable and eco-friendly practices in building and construction. Okay, as of 2021, okay, there are 47 green building certification systems across the world. Okay, for example, Green Star is the green building certification system in Australia. Finally, to conclude this webinar, let me re-emphasize the whole life approach that we can follow to decarbonize the construction sector. These are to avoid, okay, by designing better and building with less, okay, to shift by using alternative building materials, and to improve by decarbonizing conventional materials. Okay, this avoid, shift, and improve approach can assist us greatly reducing the embodied carbon in construction sector. Okay, in addition, we should also reduce operational carbon in different measures, okay, which together would hopefully eventually, okay, lead us to, okay, a more sustainable building and the construction sector. Okay, imagine one day we could all live in such kind of green infrastructures or biomaterials systems, which may no longer, okay, be the net carbon emitters, but carbon sinks, okay, that absorbs greenhouse gases emissions. Okay, we hope this day will come very soon. Yeah, well, that's all from me today. Thank you very much for your attention.
Thank you for that, yeah. Dr. Wang, do you have about 10 minutes that you can answer questions? I know you have a class to teach soon. And I want to set a timer for questions.
I think there were some questions here.
Yes. So up above, we've got a lot of stuff that have come up since then. Pema asked if we can use bamboo instead of steel for construction beams and columns for building. If yes, how much story is it feasible and not? I'm guessing what percentage is feasible for use.
Sorry, where is the question?
It's well above. Some people asked questions earlier.
Sorry, can you say it again? Sorry, I was trying to read the chat box.
No worries. Can we use bamboo instead of steel for construction beams and columns for buildings? If yes, how much story is feasible and not?
Okay, so it's about timber, right?
Yes, about bamboo specifically.
Yeah. So, well, it's actually up depending on for example, what kind of timber, the quality of timber, and so on. If you look back into our history, there are actually many buildings, high-rise building, even like towers, okay, that are purely made of timber, okay, and many of them are still standing, okay. But of course, the timber at that time, okay, and timber this time, okay, maybe different. And nowadays, we actually use engineered timber products, which actually has even better quality compared with the natural timber. So therefore, timber has very good potential to be used for even sometimes high-rise building. Okay, so now if you search the website, you can see there are also some very high-rise building using timber, okay, timber structures. But apparently, the relevant standards or regulation must be followed.
Okay. Kieran asked, is it possible to process demolition concrete into circulatory?
Circulatory. Well, I'd say recycled concrete is actually a big market nowadays. However, okay, the technology, okay, to produce high quality recycled aggregate from the demolition concrete structures, there are still some limitation that we cannot actually get very good quality concrete. Okay, but nowadays, okay, we still use recycled aggregate for example, concrete with relatively low grade. Okay, they are still in use. Okay, there are a lot of potential, as I mentioned just now. A lot of researchers are going on. For example, people are trying to use microwaves, okay, to treat the aggregate, so therefore it can actually improve the properties of recycled aggregate. So therefore we want to actually to use them to let the recycled highly cost materials to enter this circularity, I would say. Thank you. Sorry.
Okay, and then Mohammed says, what is a sustainable alternative to steel for tensile strength in reinforced concrete?
Well, I can see that there were some people talking about, for example, using bamboo. Okay, and however, okay, bamboo currently there isn't actually very strong evidence that it can be used to replace reinforcement. Okay, but in addition to bamboo, another possibility is actually polymer-based materials. Polymer like sorry, what is the name? Suddenly forgot the name. So they are actually polymer-based fiber reinforced polymer that people actually using it. They are already in the market. Okay, we have actually fiber reinforced polymer which can be used to replace rebar or reinforcement. Okay, so that is a possible alternative for the steel reinforcement.
Okay. Philippe says, is there information about how to manage the seismic performance of green concrete or green construction materials?
Seismic what? Sorry.
Seismic performance. So I'm guessing earthquakes, how it stands up
Uh,
against earthquakes.
uh, um, well, I'd say those green materials that I have been talking about is actually, for example, green concrete using relative greener concrete using supplementary materials. Okay, if you look into the performance of those green concrete with supplementary materials such as fly ash, silica film, and slag. Okay, actually, it is very surprising that the performance of those green concrete is actually better than the ordinary concrete without these supplementary materials. Okay, so even although initially people introduce supplementary cementitious materials is to actually control the cost, okay, reduce the cost of the cement in using cement in concrete. However, later on people find that using this supplementary cementitious material actually can improve the performance of the concrete, including the strength. Okay, so it indicates that it can actually performs better. Okay, so therefore, compared with traditional concrete, so this apparently would actually, yeah. So far, I'd say most of the study is actually focusing on the static performance. Okay, but if you look into the dynamic or seismic performance of material, you would see that the one who controls the dynamic performance is most probably it might be the aggregates used. Okay, so it is not actually may not actually coming from the cement paste. Okay, so I would actually expect that the green concrete, for example, using supplementary cementitious material would be almost equivalent to the performance of the traditional material when it's substituted to the seismic loading. But apparently, we need data to support this.
Yes, we do. One last question, and then we're going to allow you to leave while I share the rest of the deck with the people who have remained. Will the use of environmentally friendly materials result in the increase of building costs?
Well, I think it depends on what is the level of the technology that we are using. Okay, apparently, in some scenarios, it may increase the cost because there will be costs involved in how to collect those recycled materials. Okay, how sometimes we may have to reprocess those kinds of materials, but it is all about the regulation, the technology involved. Okay, I believe with the progress advances of our technologies, we can significantly reduce those relevant costs, and eventually we may be able to get cheaper but better and greener or more sustainable material or construction.
Excellent. Thank you very much for your time today, Dr. Wong. I know you have a class to teach, so if you would like to go ahead and go, I will show the other two slides, and I hope you really have a great day ahead of you.
Thank you. Thank you. Thank you all. Thank you very much. Yeah. Hope to see you next time. Bye-bye.
Bye. For those left, all that I wanted to share with you is the upcoming webinars page. Keep in mind that this is going to be sent to you via email. So 2 business days for the slides and the recording. Okay. So these are the upcoming courses that we have for civil engineering. So some of this topic is covered in our civil engineering courses. And this is our upcoming webinars, not necessarily about civil engineering, but these are additional free courses that you may want to join. And you can find this information on our website. But again, this deck will be sent to you. This is the code for your certificate and the QR code. Use your phone to scan it, and you can get your certificate of attendance. And again, I'm putting the link into the chat box. Please allow for 4 business days for us to distribute these before you reach out if you haven't received it. A couple people mentioned they forgot to sign up for it, but this is the way to actually get it. And I'm going to just keep this up on the screen for another minute before I end the session. And we thank you for your participation, and we hope you'll join us again for another future course.